Hey everyone, this is Akil from Oxen Academy here. This is part 5, our last part of our related rates series, and today we'll be talking about the rocket problem. So let's go ahead and get started. So, a TV camera at ground level is filming the launch of a space shuttle. The shuttle rises according to the position equation y equals 50 times t squared, where y is in feet and t is in seconds. If the camera is 2,000 feet from the launch pad, find the rate of change of the angle of elevation from the camera of the camera 10 seconds after liftoff. So, in this problem, we're actually given the diagram, and there's actually one quantity that's missing. We're given the diagram, and we're given that this horizontal distance is 2,000 feet. This vertical distance it varies with time, and it's 50 times t squared. And so therefore, we have y and x, and this angle right here is a right angle. And this angle right here, this angle theta, that is the angle of elevation of the camera, because that is the angle the camera is tilted upward to view the rocket. So we're also given that the change in time is 10 seconds, and with that information, let's go ahead and use a trigonometric ratio. So the trigonometric ratio we're going to use is tangent theta. So tangent theta, this is equal to y over x, and this is equal to 50t squared, because that's y over x, which is 2,000. So simplifying this out, tangent theta gives us t squared divided by, just go ahead and simplify, cancel out a 0, 5 divided by 200, that's equal to 1 over 40. So you get 40 on the denominator. Now, let's go ahead and solve for theta. So, theta, if we take the inverse tangent on both sides, this gives us the inverse tangent of t squared over 40. Now let's go ahead and differentiate both sides with respect to time. So, theta varies with respect to time, so let's use implicit differentiation. Doing implicit differentiation simply gives us d theta dt, but with this side, we don't actually need to do implicit differentiation because this is in terms of t already, so we don't need to put a dt dt because that's just going to be 1. So, differentiating tangent inverse with respect to the inside function, this gives us 1 over 1 plus this inside function, t squared over 40 squared, but we have to multiply that by the derivative of the inside function because of the chain rule. So this gives us the derivative of the inside, that's going to be 2t divided by 40, because that's just from the power rule. And 2t divided by 40 is the same as t over 20. So now all we have to do is let's go ahead and plug in 10 seconds for time. So d theta dt evaluated at time equals 10 seconds. This is going to give us 1 over 1 plus 10 squared over 40 squared, multiply that by 10 divided by 20. And so let's go ahead and do some simplifications. This gives us 1 over 1 plus 10 squared divided by 40, that's 100 divided by 40, which is equal to 5 over 2, just by simplification. 1 over 1 plus 5 over 2 squared, that's going to be 5 squared over 2 squared, which is 25 over 4 times 1/2. And if we go ahead and simplify this out, this gives us 1 over, multiplying a 2 into this denominator right here, 2 plus 25 halves, and this is the same as 1 over 29 halves, because 2 plus 25 halves, this is going to be 4 plus 25, all that divided by 2, which is 29 halves. And then all that's left for us to do is just take the reciprocal of the denominator, because it's 1 over, and we get 2 over 29 radians per second. And the reason why it's actually radians for this unit, that's because whenever we take the derivative of theta, or just some trigonometric function, that trigonometric function will always be in radians. So therefore, this right here is radians per second. And if you actually want to go ahead and put it in degrees per second, that would be 2 over 29 times the conversion factor, which is 180 divided by pi, and that gives us 360 divided by 29 pi degrees per second. And that is our answer. So with that, that concludes the rocket problem, and that also concludes the related rates series. I hope you enjoyed this series of solving related rates problems with me, and I hope to see you in future videos. This is Akil from Oxen Academy, signing off.